All right, so with no further ado, let's talk about treatment. We've talked about how disease was thought to arise. Now let's talk a little bit about how it was treated throughout history. We're going to jump back to ancient times real quick, but pretty quickly move into the Renaissance era. But in ancient Egypt, the idea was that disease occurred because of a flux, F-L-U-X, of bad food. That was where the concept of disease came from, was that bad food would move out of your intestines, out of your gut, and migrate around your body and create swellings, things like tumors. It would cause disease, it would cause pustules, and that to treat it you had to readjust the blood, you had to readjust the circulation, and so you could have sweating, you could use emetics, you could use enemas and so forth. Bleeding was well known. But in addition to that, the Egyptians had a pretty sophisticated kind of knowledge of pharmacology for the time. They had a lot of different substances that they'd recorded and tried to write down what they thought they were good for. Now, by modern conceptions, they really didn't have very effective medicines, but some things were there, and they had access to alcohol for numbing pain, salt, things like that. Crushed gems is one of my favorite treatments that existed throughout history. So if you want to think about primitive Goldschlager as a cure, then you've got that going there. Goldschlager is the vodka with gold in it. Your 48-year-old professor shouldn't have to be explaining that reference to a bunch of ex-college students. Now, one thing about the Egyptians is because they had such an intimate knowledge of pharmacology for the time, it's been theorized that the Eye of Horus here is actually where we get that wacky pharmacology symbol. Now, that might just be hearsay, but it's a theory that's been put forward because I've not heard anyone come up with a convincing explanation for why that pharmacology symbol got associated with the alchemists and later the apothecaries that were using it throughout time. So let's talk about Galen. So Galen, we talked about with the concepts of disease and how he theorized that disruptions of the humoral imbalance would cause the pneuma to get out of whack and cause different parts of the body to perform poorly. And he had really revolutionary, although what we would consider to be wrong, theories about how the body worked. He was really conservative when it came to treatment, and he prescribed most of the things that were fairly standard at the time: bloodletting, purgatives, sweating, and so forth. But he did really draw attention to bloodletting, and because he was so authoritative for over 1,000 years, bloodletting became one of the major routes that people would use to adjust the humoral imbalances that they would diagnose in their patients. So bloodletting was done a lot of different ways. Now, one of the most common was to use what was called a lancet or a double-bladed knife to open up some veins, and you can see an illustration of it on a Greek vase there. So they're opening up the veins, and generally the rule of thumb was to bleed someone enough that they get lightheaded. So that was the idea. And if you've heard about people being bled when they're already ill, feverish, and so forth, it absolutely happened. People who probably needed that blood really badly had it taken away from them. At least one king of England is theorized to have had a really mild malady and then died because they kept on thinking about draining more and more blood from him to arrest the disease. The most horrifying method of bloodletting to me is not the leech you see pictured on the right, but it's a thing just to its left. That's called a scarificator, and it's basically a spring-loaded box full of razors that you put up against your arm. The razors pop out, and then you get to bleed some. The leeches, in comparison, were actually fairly sterile and hygienic in comparison to this rusty contraption full of old people's blood, probably still stuck on it from the last patient. Leeches would be farmed, and there were huge leech farms throughout France that people would gather them from, and doctors would use the leeches to remove nearby congestion, take off a certain amount of blood. And interestingly enough, medical leeches are actually still a thing. They have their use in taking out edemic fluid because they have a very sterile bite, and so they are actually still used in some reasons, but we don't try to adjust the humoral imbalance with them anymore. Now, most of pharmacology has its roots in herbology and trying to understand how various natural, either plant-based derivatives or minerals could be used to heal. And for a long time, this was not known as pharmacology. It was known as Materia Medica, and in fact, the course that people would take in medical school for, up until about 100 years ago, it was called Materia Medica. And that comes from an incredibly long-lived book called Materia Medica that was written by another Greek who lived around the same time of Galen. So this is Dioscorides, and he was a physician who worked with the Roman army, traveled around, and he wrote down a lot of the treatments that were possible with various plants and botanicals that he came across in his travels. And most importantly, he wrote down how to identify these plants because, I don't know, if you're botanically illiterate like me, looking at one plant versus another is not going to be a great way to figure out how to treat someone, but by giving a really good description of the leaves, the roots, and so forth, he was able to actually get people to at least look at the proper plant. Now, this book was used in medical training up until the 1700s, and it's still in print. I double-checked that before I came in, so you can go on Amazon, buy your copy of Materia Medica, and you will be up to date on the best of pharmacology circa 1 AD. So that should be nice for you. So we discussed how medical practice and innovation left the Egyptian world, moved into the Greek and Roman eras, and after the fall of the Roman Empire, most of that learning in mathematics, science, and so forth shifted east to the Muslim empires around Baghdad and Damascus, and that's where a lot of this work was done in the Western tradition until Europe calmed down and was able to have universities develop where people could actually start learning authoritatively again. So in Baghdad and Damascus, Avicenna was one of the big names, and we've talked about him once already, but he wrote a really authoritative book called The Canon of Medicine, which basically means the entire sum knowledge of medicine. And just like Materia Medica, this was considered to be very broadly applicable and was used in medical training up until the 1800s. Now, one thing he did for pharmacology is that he broke down the substances that were used into simples and compounds. Now, simples are just going to be things derived from one plant, one leaf, one extract, whereas compounds would be various combinations of those simples. And he looked at how they could be classified and utilized. So that was one of Avicenna's big contributions to medical treatment. Al-Razi was another Muslim scholar who would kind of more likely be called an alchemist or a chemist, but had a lot of activity in medicine, or at least his applications were there, because he really pioneered what was called the mercury-sulfur theory of reality or of substances. And that idea is that if you've got a substance, it exists only because it has a certain ratio of mercury and sulfur. And if you can adjust those ratios, you can change that substance. So when you hear about alchemy, what's the most common thing people think about, aside from Harry Potter and the Sorcerer's Stone? Changing something into something else. Anybody? Chemistry, you're jumping ahead. No. You're right, but you're right too soon. What did alchemists always try to do back in historical days? What was the thing they would do to make people rich? They would turn something into gold. And if your theory of materials is that it's all a ratio, if you can adjust that ratio, theoretically you can change anything into anything. So they really did believe they could transmute base materials into gold or other valuable materials. Now, obviously, that paradigm didn't pan out. That's not how it worked. But in the process of exploring that, they came up with a lot of different processes like distillation, extraction, and I think somewhat hilariously, because the Muslim culture was not allowing the consumption of alcohol, yet these guys came up with the distillery methods that are used in production of alcohol and so forth. This is where a lot of those chemical processes were initially discovered. So his experimental approach really did set the stage for alchemy becoming chemistry. And if you think about the Arabic definite article, al-chemi just means the chemi or the chemistry, and that's where those two are connected. Chemistry is rejecting the material theory that you can transmute things, but kept a lot of the processes that were developed by alchemists. So the goal of treatment, despite the fact that we've got bloodletting, simples, compounds, the goal of treatment is still to adjust the humoral imbalances that are present. However, one modification that came up by the various commentators in the Muslim era was that the adjustment, or the balance rather, was different from person to person. And that difference existed because of astrological signs that were present at the time of our birth. So depending on where the planets, the stars, and so forth were, when we were born, we would have a different humoral baseline. And adjusting our baseline to someone else's could make us sick, whereas it could make that other person better, even though it would be something that would be bad for us. So essentially they're stating that everyone has a different baseline for their, shall they say, profile of how the humors should be interacting. Now, another material theory that came up with this is that they felt that the mercury-sulfur theory would adjust how different things became what they are, but different metals occurred because that ratio is adjusted by the light from each planet. And so if you had sunshine hitting some undifferentiated material, it would make it into gold, whereas moonlight would make it into silver, and the light or influence of other planets would cause the metals to change into something else. Now, this was something that actually dovetailed nicely with the significant contributions that the scholars in Damascus made to the study of astronomy. So astronomy and astrology initially were very similar to each other, and ancient astrology is not the same thing as, the astrological signs we see in the newspaper. It was a very rigorous set of practices based on keeping records. Now again, by modern standards, it doesn't really correlate to a causative action on anything, but they were very serious scholars, and without those astrologers keeping track of things, we would never have astronomy or the actual study of celestial motion. So just remember real quick and file away that different metals occur because of the influence of the stars. Different humoral compositions occur in individuals because of the influence of the stars, and we'll see a little echo to that when we get to miasma and bad air. So we've got what is going to become modern science continuing in the Muslim empires. Things have kind of fallen apart in most of medieval Europe. There are a few bright spots, and we'll get to those in due course. But basically, medieval Europe had pulled back a little bit from that exploratory, experimental model that was used by people like Galen. And so supernatural judgment, demons, sin, and poor choices by parents were blamed for the things that cause disease for people. One thing I thought was really interesting is that one theory of malformations that would occur if a child was born with a malformation, they said it was because something scared the mother while she was pregnant. And they said somebody with a cleft lip must have been the mother must have been scared by a cat when she was pregnant, or somebody who had a clubbed foot had the mother scared by something that made her think about feet, and it was thought that those malformations were due to influence from the outside based on what the mother experienced. So the physicians and surgeons, which we'll talk a lot more about next time, who were active at this point, maintained that separation that the Greeks had put in between intellectual work and manual work. The physicians were the intellectuals. The surgeons and the barbers were the people who actually did the work. And the physicians did their best not to touch their patients or even really be around them. They wanted to just if you think about that stereotypical, hands-off doctor, looks at the chart, doesn't even glance at the patient, rockets out of the room as quickly as possible. That person is actually doing a really good job of impersonating what physicians were for hundreds of years. Now, one therapeutic that was used pretty widely was called the urine wheel. And you can see an example of a urine wheel right in the center. And the physicians would look at the urine that was gathered from the patient, swirl it around, sniff it, maybe even take a little taste test to see if there was sugar in there. But essentially, they would look at the urine as a guide to where illness was, then consult their urine wheel, see where they thought the person might be imbalanced, and then come up with their diagnosis and possible treatment. Now, the physicians were not going to be touching the people and certainly not going to be affecting any actual hands-on cures. So the people who did that were barbers or barber surgeons or surgeons. And the terminology used varies from place to place. And on the right, we can see a barber actually helping someone pass urine with use of a catheter. So at this point, we have a very clear distinction between manual surgical work and intellectual physician work. Now, I see these a lot, and I have no idea why physicians are often shown with these pair of like scarf breasts, but you'll see it a lot. So if anyone comes up with an explanation for what that's all about, please do let me know, because they're in a lot of illustrations of professors and physicians in the Middle Ages. Now, as we know, looking at urine actually can do some halfway decent things. Diabetes can be diagnosed by the amount of sugar that's there. Actually, in India, the diabetes was actually sometimes diagnosed by putting urine on the ground and seeing if ants came up to it afterwards to diagnose that there was actually sugar in there. But you can look at urine and see differences. You can see a UTI on the left side there. Myoglobinuria, what's going on there? What's hanging out inside that urine? Muscle proteins, yeah. So overuse of the muscles has gone through the filtration apparatus of the kidney. And hematuria, that's bad news. What's in the urine there? Yeah, so blood in the urine. So looking at urine as a diagnostic tool, once again, not a bad idea, but it was being used under a paradigm of treatment and paradigm of disease that really didn't let them explore what was going on with an open mind. It was more about trying to diagnose how these color changes could be used to create a humoral diagnosis of where they were imbalanced. Now, no talk about disease and treatment in the medieval era is complete without talking a lot about the bubonic plague, the Black Death, the Great Mortality, and essentially the bubonic plague came from fleas and rodents living in the steppes of Asia, in the Mongolian area, but as travel was occurring more frequently, the rats and fleas were riding along with those groups. And there was a group of Mongols who were besieging the city of Kaffa, which is on the coast of the Black Sea, and they had a plague outbreak and had to break camp and leave. But before they left, they engaged in what's thought to be the first ever use of biological weaponry in warfare, and they catapulted some of the dead into Kaffa, where another plague series broke out. Italian traders from Genoa left Kaffa, went back to port in Italy, and the disease did a very modern thing. It didn't spread overland as frequently as it spread from port to port to port. It would actually jump according to the trade routes that were present there. And because no one had any idea what the route of transmission was, it was very difficult to control that. Now, plague would spread overland, but much slower than it would jump from port to port to port. Iceland nearly avoided it because they realized it was coming a long way before it got there, but it finally worked its way in kind of a counterclockwise rotation all the way from the steppes of Asia through Africa, Africa, Europe, and back up into Russia before that first outbreak really got finished. So, people did not know about rats and fleas being the vector of this disease. So what did they blame? They blamed divine punishment. They blamed Jewish communities living in the cities or in the countryside, and interestingly enough, the Jewish communities in the cities were often so dense they had a greater than average death rate due to plague, but this didn't seem to placate or at least kind of occur to anyone who was persecuting the Jewish communities. And one thing that caused them to sometimes be even more suspect was that in the countryside, a lot of Jewish communities actually had lower plague rates than their neighbors, largely because of the hygienic practices that were employed, sweeping out the floors every so often, and just generally keeping grains and other things away from where animals would be able to get at them freely. Now, in addition to that, there was a contagious theory of disease, which was really poorly enunciated, but it was basically thought that disease can spread from person to person, but no one really knows why. So they were kind of on the right track with that. But the most prevalent theory was that the disease was caused by bad air, or miasmas. And this bad air occurred because, just as the stars can shine down in these theories, on the alchemical theories, can shine down and create metals, sometimes the influence of the stars creates poisonous gases that are trapped underground. And when they're exposed to the air, they spread across the countryside and caused disease. So that bad air, or miasma, was thought to be released from underground, and that actually is not as kind of fanciful as it sounds. Think about miners, people who were working in the mines, who were trying to, get coal, get other metals. They would occasionally hit big pockets of carbon dioxide, and what's going to happen to them? It's not pleasant. What are they going to do? You're being very nice. Pass out is close. They're going to die. So they knew there were poisonous fumes underground, and the idea was that they would be released, and that would be what would cause disease. So that was one of the things that was thought to be causing the Black Death. Now, once again, they didn't really know. They had no effective means of stopping it. I think Venice was only one of the few cities that actually managed to do it well, and that's because they instituted a massive quarantine on anyone coming and going from the city and kept them there in quarantine for long enough that they would die of the disease if they had it before they had a chance to get to the city proper. So, how do you fight bad air? If that's what we think the disease is, you fight bad air often with good air. So people would walk around with flower petals, spices, oils, and the plague doctor mask that we see pictures of, it's a beak that's not, strangely, it's not put there to terrify people. That's just an after effect of it. But essentially that beak is there so you can put flowers, spices, other pleasant smelling things in there because it's thought that the pleasant smells would combat the bad smells. In the process of coming up with these permutations of the plague doctor outfit, they weren't intending to make a medieval hazmat suit, but they basically did. They had gloves, oiled leather, large boots. They would use a probe to contact people. They wouldn't touch them directly. So these plague doctor suits actually did a decent job of protecting the doctors, but not for the reasons they thought it did. They thought it kept out the bad smells. It wound up actually keeping some of those fleas off them as they were examining their patients. Real quick though, this picture of a plague doctor this style of it that we usually see didn't come around until about the 16th or 17th century. So they had elements of that earlier in the medieval era, but we didn't have plague doctors running around in medieval times looking like this with the hat and everything, just little bits of it. So, the Black Death eventually burned itself out. Any disease that's that deadly can't maintain enough of a host population to actually stay around. It has to be a lot less deadly to maintain enough people to actually spread it. And the people who are left after a pandemic tend to have some immunity to it. The ones who survived often survived because the disease wasn't as able to get into their cells. So bubonic plague would return to Europe and Asia over and over, but never quite as severe as that initial outbreak in the 1300s. Now, after the Mongols, who again had brought plague to the Black Sea area and to the Genoese, had also been destroying areas of in the Muslim empires, had been sacking Damascus, had been sacking Baghdad. The scholars who were there, Jewish, Islamic, and even Christian scholars who were working in those empires had to flee somewhere else. And so they fled to Europe. And Europe, as we talked about last time, had developed universities. Small institutions that actually usually formed around a single scholar that just had students kind of flock to him or her, sometimes her very infrequently, but it did happen. And then as scholars would kind of cluster together, they would become more stationary, and the universities would actually become a place rather than just a gathering of people. So with these universities, the scholars who were fleeing the destruction of those cities brought texts with them that were in the original Greek, much more accurate, much more complete, some works that people in medieval Europe had never even heard of or had only heard about in reference. And so it was very, very well received for these scholars to move to the universities. However, we're still working with the same status-based hierarchy. And at this point, people working with their hands are again not treated as though they're actually that skilled compared to those who are intellectual and are thinking about things and doing physician work. And one of my favorite examples of this is that the physicians in medieval Europe were signified their status by wearing long robes. They had long robes on. And the barbers and the surgeons had to wear short robes to kind of show that they weren't quite as cool as the physicians. Does this ring a bell to anybody thinking about your your cute jacket white coats versus the long lab coat that you get when you magically become a doctor. My favorite aspect of this is there was a group of surgeons in France who decided they wanted that high status, and so they stopped practicing surgery and became theoretical surgeons who read their Avicenna, read their Aristotle, and tried to ape or kind of mimic the high status physicians, and they would also wear a long robe. So what's kind of funny is we had these surgeons moving away seeking status when in fact, from our point of view, the people who were actually doing the work of examining people and treating them were the ones who were actually poised to make actual discoveries that would have an impact after we switched from the humoral paradigm to a modern paradigm of organic and tissue-based disease. All right, so another great thing about medicine in the Middle Ages is that we had no science. Science in terms of an actual human activity doesn't really get formulated into something like its current state until really the 1800s. And before that, people were referred to as natural philosophers. They were studying some aspect of nature. And in the Middle Ages, one of the most prominent ways people would study nature was by studying what was called magic. So magic was thought to be an examination of harmonies that exist within nature and how they can be used to our benefit. So that was thought that magic could be used for good or for ill, so black magic, white magic, etc. And it was just really knowing the correspondences and relationships between structures of the world that had been put there by God at the time of creation. So that's where magic was. Magic wasn't considered to be a bad thing, but it could be used for bad purposes, and that's why witchcraft, sorcery, and things like that were not allowed by the authorities at the time, but exploration of magic was actually something that was done in most of the courts of Europe. So the big theory that undergirded it was called the doctrine of signatures, and that's the idea that God had left evidence of creation in the relationship of these things, and you could use that to help treat someone. So, believe it or not, it's now time for magical case studies. I don't have any turning point slides, I'm so sorry, but you can just kind of click in your mind. So, a knight is constantly feverish and phlegmatic, producing snot, copious nasal discharge. This humoral imbalance is brought about by excess phlegm weakening his brain. What dietary intervention might the doctrine of signatures say we should give this person to help treat his phlegmatic disposition? Give me some ideas. Naturally, this is not for credit, although that would be awesome. So what can you feed somebody who's got a weakened brain? What would the doctrine of signatures suggest? Even the right answers are wrong, so go ahead and just say anything. Broccoli. I like broccoli. That's not bad. Why do you think broccoli? It looks like a brain. You're absolutely right. So broccoli could be there. The big one for this sort of an ailment, walnuts, because walnuts also look like a brain. Okay, good job. Magical case study number 1. Next one. A Venetian merchant has a naturally cold disposition and needs to eat more warming foods. However, the Ottomans have blocked Constantinople and are throttling the supply of spices that would other innately hot foods. What other sort of food might be advantageous to someone who has a cold disposition and needs to be warmed up? Well, I already got spices. Spices aren't happening. The Ottomans have blockaded Constantinople. Soup. Okay, so hot soup. That's not bad. What's the hottest thing there is? Oh, even hotter than that. The sun. What kind of foods would make you think about the sun? How about sunflowers? These flowers like to even look at the sun. They're watching the sun go across the sky. So you think, okay, well, I can't get hot spices, so I'm going to get something that is suggested of the sun, sunflower seeds. That's what I'll feed this person till we can get curry back on the menu. All right, so this is pretty much what the doctrine of signatures would be used, this is how it would be used, rather, to treat people in various ways. So that's how it worked. Anybody want to ask me about sword balm? What's sword balm? Glad you asked. Okay. So the doctrine of signatures held that there was affinities between the things that created disease or injury and the injury itself. So if someone was stabbed and they were falling on the floor, bleeding, and the knife was nearby, someone might really run down, grab the knife, and instead of putting ointment on the person, they would put ointment on the sword, or ointment on the knife. It was called sword balm. And the idea was that there were some, very fine particles still connecting the action of violence to the implement of violence, and that somehow by calming the sword, you would calm the wound that it had caused. So that is sword balm. So just be aware, that was the idea at the time. So I just really enjoy the thought of quick, get this sword to the hospital, stat. This man's dying, quick, get the sword out of here. All right, now another name that comes up in the process of refining alchemy to become a little bit more like modern chemistry is Paracelsus. And Paracelsus may have the greatest name of all time. If we read his whole name out, and I always have to refer to it, Philippus Aureolus Theophrastus Bombastus von Hohenheim. So you can see why we call him Paracelsus. So Paracelsus was Swiss, and he's considered to be the father of toxicology because he's the first person who was really on record as saying that things are not innately poisonous or not poisonous, that it's the dosage of that thing that makes it helpful or harmful. So basically saying that there are things that we can use to treat people, but we have to be very cognizant of exactly how much of it we're giving to them. He studied everything. He was a real, wide-ranging scholar. He studied metallurgy, alchemy. He actually went down into the mines. He really despised the academics who read their books all day long and, in fact, would open up some lectures sometimes by burning copies of Aristotle or Avicenna. This is before the printing press. This is actually not a minor, financial thing to do. But he would really prized the idea that people who worked with their hands knew more than the people who only read books. And he enunciated some theories related to alchemy and said that in addition to mercury and sulfur, you also had to factor in what was called salt, not sodium chloride like we think of salt, but fine-grained kind of precipitates that could come out of different reactions. So he lectured in German, not in Latin, which was kind of also a bit crazy, and he was a real iconoclast. He didn't really play by the rules at the time, and it really came back to bite him because he made so many enemies. He just had to hop from town to town with his students kind of following him along. And one of my favorite little bits of trivia about Paracelsus is that all the books and all the works attributed to him are thought to have not been written by him, but by his students transcribing what he said as he drank in various taverns, and they were just trying to catch up with what he was saying along the time. So there we go. So he got in a lot of legal trouble. He really made a lot of enemies, but he really was a breath of fresh air in terms of looking at things with a fresh eye and essentially trying to figure out how manual labor and knowledge of craft could be brought into the practice of medicine. Now, around this time, we've talked about the University of Padua being a place where anatomy was being studied and becoming a little more of an actual proto-science. At the same time, Padua did a very interesting thing with its Materia Medica curriculum. It instituted its own botanical garden strictly to grow medical crops, medical fruits, vegetables, herbs, and so forth, and it actually still is there. It's on my list of things to do if I ever get to Padua, is to check that out because it's still in existence, and it was the first botanical garden just for medical treatment and was used for training the physicians and treating the patients who came to the University of Padua. Now, we're jumping forward a bit because we're getting closer to modern science coming after the era of the Enlightenment in the 17 and 1800s. And at this point, people are getting a little more willing to question old authority. They're more willing to look at things in a slightly different way. And I'm going to screw this up. I always try to get it right. Pharmacognosy. I got it right on the first try. Pharmacognosy was one of those early examples of it. And it's basically looking at botanical preparations, seeing what makes them effective, and trying to standardize their treatment. So William Withering is experimenting with foxglove. Now, foxglove is a poisonous plant. However, it can actually help people who are experiencing heart failure. At the time, it was called dropsy. So people with dropsy would have heart failure, they'd have a lot of edema, a lot of swelling. It would be very difficult for their heart to pump blood through their bodies. And foxglove could actually help them get some of that fluid off. Now there's another problem though. Foxglove, sometimes it's a little stronger at other times. Maybe the time of harvest or how long it's been since it was harvested can make the active component more or less active. And what's the big problem you run into if you're giving someone the wrong dosage of foxglove? You can kill them. So people had known for a long time that foxglove could be used to treat people with dropsy, and this was something he learned from a woman herbalist, someone who we'll never know the name of, because women were largely relegated to kind of, I don't want to say behind the scenes, but kind of low-level medical practice, because if they got very prominent, they would be shut down by the authorities. But essentially, he did take seriously that observation that it could be used, and he figured out how to dose it, how to prepare it in a way that would stop people from dying, and this is where we get digitalis and digoxin from. It's actually still used to treat heart failure, but we've isolated the individual components that really allow it to work, and that process is pharmacognosy. It's actually looking at how you get drugs from those naturally occurring substances. So we've entered the Enlightenment, and the Enlightenment not kind of really took off with the idea that you can question authority, and pretty soon people were coming up with all kinds of new ideas. Now, the great thing about new ideas is some of them are insightful and amazing and have lasting contributions, but what else can happen when you have a lot of new ideas? Some of them are crap. So you don't know, though, until you explore them, investigate them, and see how they work out. So people in the Enlightenment were coming up with all kinds of new observations on how things could work. So one thing that the Enlightenment proto-scientists, the natural philosophers, were really into was something called imponderable fluids, invisible, undetectable fluids that somehow permeated nature and allowed things to happen. So my personal favorite is phlogiston. Phlogiston was the fluid that allowed things to burn. So if I held up a log of wood, you could say that that log is absolutely saturated with phlogiston. It's just got phlogiston in every crevice. Then I burn it, and the ashes have been dephlogistonated. The phlogiston's been burned away because it's been what allowed it to burn. So phlogiston theory didn't really hold up. Chemistry kind of put that to bed. But there were other imponderable fluids that were a little more interesting in terms of the development of modern science. The first one was animal electricity. Galvani figured out that you could use electrical current to cause muscle contractions. He had frog legs, and they were able to actually move, even if they were removed from the frog, if they were stimulated with an electrical charge. Another guy you've probably heard of, Volta, realized that you could do the same thing with chemical compounds, meaning that chemistry and electricity were connected, and so that it was a chemical reaction that caused the electrical discharge that caused the contraction of the frog's legs. Electrical fire. Anybody heard of this one? Electrical fire is another imponderable fluid, and it's actually electricity. So that one actually worked out really well for us. So electrical fire. Now, when we think of Ben Franklin, when I say Ben Franklin, what's the first thing that jumps to your mind? Give me a phrase or a word. Syphilis. Okay. Uncommon answer, but okay. Someone else. Ben Franklin equals? Bifocals. Okay, good. I was hoping you guys would shout Founding Father, but you have to ask the question. So in America, Ben Franklin was known as a politician, a representative, but throughout the world during his lifetime, he was more known as an inventor and what was known as a polymath, somebody who was really brilliant in a lot of ways. So the invention, or at least the observation he made that electricity and lightning were one and the same, allowed him to design lightning rods, and prior to that, having houses and churches and other things burned down, it happened a lot. But now that things are designed with lightning rods installed, there's a path that electricity can follow to ground itself that doesn't have to go through flammable objects. So this is our just illustration of Ben Franklin discovering the connection between lightning and electricity. I don't know if there were that many cherubs actually present at the time. And if I'm going to be honest, my personal favorite representation would be Ben Franklin actually stealing it from Zeus himself. So this is my preferred rendition of how that worked. So basically, we've got those electricity as one of those imponderable fluids. And one you may not have heard of as an actual thing is animal magnetism. Now, when you hear about that now, it just means somebody has real charisma. People like to listen to them, they like to hear what they say. But animal magnetism was one of these imponderable fluids that was theorized to exist by a guy named Franz Anton Mesmer. And if you think about being mesmerized or having someone really kind of hypnotize you, it's come from his name. That's where this comes from. So Mesmer thought that there was an imponderable fluid going throughout the whole universe called animal magnetism, and that if people had internal blockages, it would impede the flow, make them ill, make them have nervous, anxious disorders, and so forth. And what's interesting, using his theory, he was actually able to cure quite a few people. He was able to cure people who had a lot of nervous disorders, some psychosomatic things, and he really did set the stage for hypnotherapy and modern psychoanalysis. However, Mesmer was not willing to look at the results apart from his theory. And the theory of animal magnetism is very complicated, very contradictory internally, but he said there could not be any other way things work other than animal magnetism. And when animal magnetism was shown to be absolute, garbage, his contributions that could have been gained by focusing on his results and explaining them in another way were really lost. Interestingly, he would basically have he'd hold his hands over people and they'd say they felt warmth there and so forth, and a tribunal was convened by the King of France to see whether there was any truth to this. So one of Mesmer's most advanced students came over to do that, and the tribunal would have him work on somebody, and they'd say, oh yes, I feel the burning in my arm as he moves his arm over it. Oh, I feel it in my back, he's moving his arm near my back. So one of the members of the tribunal said, let's blindfold the people. And suddenly they were describing feeling the flow completely different from where the person was pointing, completely separate from what they were doing, and it was shown to be just a product of their mind. And by the way, the person on that tribunal was Ben Franklin. So he was in France at the time, and I have this book. It's a children's book I got for my kids about that process of animal magnetism being disproved by Ben Franklin. So he insisted on theory over results. And whereas throughout most of history in Europe and development of medicine until then, theory predominated over counter-observations, we're now at the point where it's no longer good enough to have a theory that doesn't stand up to scrutiny. People are now starting to look at things and really holding them to account to explain what they claim to explain. So, we're now also trying to figure out how to assess the health of patients. If you remember last time, we talked about Giovanni Battista Morgagni, understanding how organs can be the location of various diseases. So if diseases can be caused by problems in organs, how do we find out that these organs are healthy or not? There's no x-rays. There's no way for us to look directly at the organs until the person's passed away. So the French came up with what is now the modern physical exam. They really worked to make the basis for that. And the first person who really kind of came up with a method of physical examination that could tell you about the state of an organ while someone was still alive was Jean-Nicolas Corvisart. And he, in addition to coming up with physical exam, also instituted the grand rounds method of teaching students by going from room to room, discussing the prognosis, the findings, and the probable outcome of a patient. Now he came up with the idea of auscultation, percussion, to check the fluid in lungs to see if there was pneumonia there and so forth. And he came up with this because his father was an innkeeper who regularly had to figure out if there was enough wine left in various casks. So he would tap it, listen for dullness, like, okay, wine's still pretty high here, we can work with that. And he applied that same theory to examining someone's thorax. He had a student who surpassed him, and in a good way. This was going to be René Théophile Hyacinthe Laennec. Now, Laennec was an unhealthy person. He was very active, very energetic, but he kind of grew up small. He didn't have he wasn't very healthy. He contracted respiratory diseases fairly regularly, but he was a very conscientious student, but he was also very shy. And one day during grand rounds, Corvisart asked him to examine a patient who had come in. Now, this very shy country boy has just been asked to examine the patient, which means he has to go to this woman who is an overweight prostitute who's come into the hospital. She's sweaty, she hasn't bathed for a while, and he needs to examine her heart by doing it the only way they know how, which is by sticking his ear up to her chest. And this shy guy just freaked out and had like a panic attack and ran out of the room. However, he was able to redeem himself because while he was outside, he saw some kids playing a game he remembered playing as a kid, where they would have a stick of wood, they'd put it up to their ear, and somebody would kind of scratch at it, and they could hear the scratches. So he thought, hey, I can get a stick or something and put it on her chest and listen to that. So what finally happened was he rolled up some paper, put it to her chest and listened, and his surprise, he couldn't just hear it okay, he heard it better than sticking his ear up to the patient. And as an amateur woodworker, he decided to start making round tubes. The original stethoscopes were these rounded wooden tubes with a bell on the end, and they have now become the universal symbol for I am a doctor. Now, what I love is that he wrote a book about respiratory diseases, and if you paid a little bit extra, he would hand lathe his own a stethoscope just for you, and you could have that. So that'd be a nice little thing to have, is a stethoscope made by the person who invented it with a copy of the book. Now, he did a great deal to diagnose respiratory diseases. The stethoscope became, fairly fashionable, although some people thought it distanced the patient from the doctor, but because the results were better, it became useful and people adopted it fairly quickly. Now, sadly, he passed away from tuberculosis, which he contracted by treating so many tubercular patients at the time. And so a disease that he had done a lot to diagnose and treat eventually took his life fairly early. All right, so now we're going to hop and skip around a little bit from topic to topic. We're going to start at how microbiology and the ability to treat infectious disease came from one of humanity's oldest scourges to the modern era. And I think we can really start this fruitfully by talking about smallpox. Now, smallpox is an incredibly nasty disease. Evidence of it has been with us at least since ancient Egypt, if not before, and there's descriptions of it in Egyptian, Chinese, Indian, and Sumerian kind of medical texts. So smallpox basically causes large pustules that come together, and slough off a lot of skin. You can get secondary infections from those rupturing as well, but the smallpox bacillus is actually pretty nasty on its own, and it tended to be fatal in 30 to 40% of people. So think about a disease that's existed and kills off 30 to 40% of the people you know regularly all the time. If you live long enough, you're likely to get it, and if you're lucky, survive it, but probably have some scarring as a result of it thereafter. Now, people had realized that variolation, taking smallpox crusts and pricking people with them, could actually confer immunity. This was first discovered in China, and it spread through India, the Middle East, and Africa. Interestingly, it bypassed Europe. This is one time Europe got completely bypassed. But this process of variolation could provide lifelong immunity to smallpox. But what's the downside? If you poke somebody with some crusts of smallpox, what's going to happen every so often? They're going to get a full-blown case of smallpox and die. So it can confer immunity, and the bacillus that were in these crusts tended to be relatively weak, didn't quite attack it strongly, but variolation could, in fact, cause death. So variolation bypassed Europe, and in fact, only came into knowledge of those of European descent after it came to America. Now, Cotton Mather, who you might have heard of as one of the people involved in the Salem witch trials, was a Boston clergyman, and he had a slave whose actual name is unknown to us. He was referred to as Oniismus, but he had learned variolation from where he grew up in Africa, and basically taught Cotton Mather, yeah, you can take those crusts, prick people with a knife or a pin, and induce some immunity. And Cotton Mather thought this was a good idea and encouraged people in Boston to get it done. People were actually either for it or against it. And in fact, his house was firebombed by people who thought he was doing something really immoral by encouraging this variolation to happen. But it definitely did decrease the significance of an outbreak that occurred in Boston in the 1720s. And the process became so well known that in the 1770s, George Washington insisted that everyone in the Revolutionary Army be variolated and actually have that done. And it's thought that the health of the Revolutionary Army, because of that, was actually pretty significant, and that one reason we lasted through the Revolutionary War is that we didn't lose as many soldiers as we would have otherwise. So that's one of the pivotal things that occurred involving military hygiene rather than military tactics in the Revolutionary War. So, variolation exists, but has problems. Actually, in some of the European courts, they had family who were in Russia, and they would actually learn about variolation from the Russian cousins, but it was definitely not something that was widely spread, and smallpox was a huge killer of people throughout history. Edward Jenner was a British country physician who'd actually trained with one of the greatest surgeons alive at the time, a guy named John Hunter, who we're going to talk a lot about during the next session. But he was corresponding with him and said, yeah, there's this superstition here that milkmaids never get smallpox, and it seems to actually be true. Milkmaids would always get a case of cowpox from the cows that they would milk, and it would cause some small blisters to occur on their hands, but it was never fatal. It was a very mild disease, and yet it seemed to confer immunity against smallpox. So Jenner took some of the the cowpox crusts and inoculated a child, and then later the child was variolated to, give him the contemporary treatment for smallpox, and he didn't develop any symptoms or any real problem from the variolation. In fact, the variolation didn't induce even a mild case of smallpox. It induced no case. So Jenner realized that you could actually confer immunity to smallpox by giving people a case of cowpox, which was much more mild. So this was something exciting, and he was able to spread the word, and he published his findings for free, widely spread so people could make use of it, even though he was encouraged to keep the secret and license it to people, but he knew that this would be a major boon to society. So this is one of those instances where we can say, yay, somebody did something good and public-spirited and not awful in the history of medicine. So thank you, Edward Jenner. Now, when you start pricking people with cowpox and giving them cow plasma and things like that, how's the public going to react? This is pretty much summarizing it. People thought, oh, you're going to grow a cow head, you're going to have horns, you're going to have hooves coming off your feet because you're giving yourself this cow blood, etc., etc. So I don't know if this is a good thing, but if you read about the reaction of people to vaccination with cowpox, it makes contemporary vaccine hesitancy look almost rational. Just almost. And by the way, vaca means cow, and that's where vaccination comes from. It was because we would inoculate ourselves with these cowpox crusts, and we've lost the cow, but we still call it vaccination. All right, we talked about Louis Pasteur briefly, and talked about how he was instrumental in understanding the germ theory of disease and how small, microscopic animals, in this case bacteria and viruses and so forth, could cause disease and be the source of things rotting. And we talked about how he was able to save the French beer and wine industries, save the silk industry. But one of the most famous things he did was that Louis Pasteur, working from this knowledge of vaccination and the knowledge that was gained through variolation, worked on trying to find a way to weaken existing diseases, and he worked on rabies. Now, rabies, to this day, is an invariably fatal disease. I think there are maybe 2 case studies in all of history of someone spontaneously recovering from rabies. It's a horrible, horrible disease. So it's been around for a while. He figured out a way to weaken the rabies virus, although he didn't know it was a virus at the time, but he was able to weaken it such that the body could mount in a response to it and then fight it off. And he was able to actually test this a little earlier than he expected, because a little boy who was defending his sister and some other children from a rabid dog got mauled, bitten very badly, and it was basically known this kid is going to die. So he treated the kid with some injections of this serum that he'd come up with to help fight off the rabies, and it worked. And this doesn't get enough appreciation. This is the first time an invariably fatal disease was actually reversed. It was actually stopped dead in its tracks in human history. And Louis Pasteur was a really good showman. He knew how to publicize his findings, and good for him. He was able to get that done and make sure people realized that this really was a huge step forward. And he didn't really keep himself apart from the work. He was in there getting saliva samples from rabid dogs, which you can imagine not the best. I don't think OSHA would approve of the way that they went about it at that time. So yeah, let's add it up. So Louis Pasteur cured rabies, saved the French beer and wine industries along with the silk industries. Louis Pasteur may just be the best person ever. Opinions vary, but let's put him on the list. All right, so now we've got this long history of materia medica, most of it garbage. The famous quote is kind of attributed to Oliver Wendell Holmes Sr., a famous physician in Massachusetts. Basically, he said, "I firmly believe that if the whole of materia medica could be, I'm having trouble reading it, sent to the bottom of the sea, it would be better for mankind and all the worse for the fishes." Basically saying the stuff we're using has no effective basis. There's some stuff in there that might work, but it's mixed in with a bunch of stuff that's just garbage. It does nothing. So people started looking more critically at what was being used and trying to find ways to bring what was now chemistry to bear in the process of creating cures. So Friedrich Wöhler was one of the first people to do something not really medically related, but it was an important step. He synthesized urea. A big debate at the time was whether or not organic living compounds were functionally and completely different from inorganic compounds. And he showed that you could create a living compound. Urea is created and derived from animals, but you could create it through inorganic means, meaning the chemistry is the same. Claude Bernard discovered that you could actually get extracts that would affect the body in various physiologic ways, like curare can block the neuromuscular junction. And now we're finally getting to the point where actual pharmacology is coming into play as chemistry and botany and medicine are brought together. Now, Claude Schmiedenberg basically founded modern pharmacology with his work building off these predecessors by showing that muscarine, which was derived from plants, could have the same effect as stimulation of the nerves that are going to the heart. So muscarine could have the similar effect of stimulating the vagus nerve, meaning that there's a chemical basis for nervous innervation of different organs, and he published this in the outline of pharmacology. And then one of his students, John Jacob Abel, founded the American Society for Pharmacology and Experimental Therapeutics. That organization is still in existence, and he looked at a lot of different things. He would extract various organic compounds from adrenal glands, from different tissues. He discovered histamine, crystallized insulin, came up with the idea that you could actually crystallize the insulin and eventually could be used to treat, although that took a few more steps to be effective. But this was how chemistry and botany came together to create pharmacology. Now, at this point, everybody went nuts looking for new and exciting things that they could find that would have effects on the body. And so all these botanical compounds were being studied and compared, and one that was very interesting to a lot of people was cocaine. So we find that the coca leaf has some really interesting properties, and people try to figure out what things are in that coca leaf doing that. So Carl Kohler was an optometrist who, had trouble doing eye surgery. Now at this point, if you're like me, you think to yourself, wait a second, there was eye surgery before there was anesthetic? And yeah, I don't know how, but there was. And he applied a cocaine kind of topical solution to numb the eye, meaning you could then do a procedure on it without the person blinking, fighting. I mean, you can try to hold your arm steady for a procedure, but imagine trying to hold your eye steady and not wince when something's cutting into it. So he found that cocaine would numb the eye, you could allow procedures to happen. Ophthalmologists and optometrists who'd been working on this forever realized this was a huge step forward, and cocaine became a very important topical anesthetic. Now, he was put on to the use of cocaine as an anesthetic by another student he knew who was in Vienna. This guy was really convinced he could find a new and exciting use for cocaine, and he thought it was going to be something he could use to get people off of morphine. And he was actually really upset with himself that he missed the topical anesthetic properties of cocaine in the midst of his focus on using it for therapeutics. Now, that was Sigmund Freud, so he did okay for himself later, but he did get addicted to cocaine in the process of learning how to use it and missing the fact that it was a great topical anesthetic, and it was later explored for peripheral nerve blocks and things like that, which we'll talk about next time also. So, jumping around a bit randomly now, we have antibiotics coming around in one of the happiest accidents of all time. We have Alexander Fleming leaves out a petri dish with some staphylococcus on it and finds that it got contaminated by some mold, penicillin mold, which interestingly made these little halos of lysed bacterial cells around it. This mold was making something that killed off the bacteria, and knowing that bacteria cause disease, he thought that maybe this could be a therapeutic route. However, he thought, well, it's probably not going to survive in the body, so I really shouldn't bother, and he put it aside for a while. But he later came back to this idea and tested to see if penicillin could in fact cure bacterial infections, and it did. Now, creating penicillin and isolating it and concentrating it was very difficult to do. And researchers had difficulty getting enough, but every study they did, especially one of infants who had gonococcal infections of the eye, showed that it was very effective at treating it. We now know it stops the bacteria from replicating and gives the immune system time to attack it. It doesn't really kill the bacteria, but it does stop them from proliferating. And there was a nightclub fire in Boston that people who had massive burns were treated with penicillin and were able to not get the inevitable infections that would have otherwise occurred. And the US government took notice of this because World War II had just started, and they knew there were going to be a lot of fatalities, a lot of injuries, and if there was a way to reduce the number of infections that happened as a result, it would be very good for the Allies. And it was. They started working very hard to create a lot of penicillin, and 2.3 million doses were ready in time for D-Day, and thanks to Margaret Hutchinson Rousseau, who was an MIT graduate engineer, she came up with a process to make penicillin more effectively, more quickly. And let's just take a moment and bask in the glory. It's our third session. Here's the first woman whose picture is up on screen, so hooray. And if that weren't good enough, she also figured out how to make rubber synthetically, which was something that the Axis, the Nazis and Japanese, had a kind of lock on natural rubber plantations, and so this was another way that the US war effort was supported, saving soldiers' lives and creating synthetic rubber. So, thank you, Margaret Hutchinson Rousseau. All right, now, we've talked a little bit about vaccination. Another avenue that was explored after we understood how we could create sera against things and actually generate vaccines was to look at different diseases. And Jonas Salk is the person who's credited with coming up with a vaccination process that could stop polio. Now, polio, like smallpox, has been around as long as we've had recorded records. There's a picture of an Egyptian with a kind of withered leg. We can see in the middle a man who's actually got polio as well, with the same basic affliction. And Salk took the polio virus and weakened it by including formalin, basically, kind of a modification of formaldehyde. This weakened and killed the virus, but left its surface antigens exposed so that when it was injected, people's body could mount an immune response and come up with antibodies against poliovirus without risking an actual infection. Now, injecting formalin into your body doesn't sound that good. And yeah, if you took a vial full and injected it in, that'd be bad. But formalin is actually produced naturally by the body in minute, degrees. So this isn't as awful as it sounds. Plus, you've also got the ability to titrate it out. And other processes are now used to get to those epitopes, like RNA-derived vaccines. I think we've all heard that. Anybody unclear on? Okay, I'll just go for it. You can have the formalin, lock the thing so that your body can recognize it, but you can also produce the proteins on the outside of a virus, like coronavirus, give those to the body to create, but it doesn't create any of the actual virus, and you mount the immune response to those so that when you see the real thing attached to the virus, you can fight it off. Everybody on the same page? I see nodding. Very good. Now, I'm jumping around once again. I don't have a nice clean transition here, but another treatment method that really doesn't get as much wow factor as it should is CPR. Cardiopulmonary resuscitation is a relatively recent creation. It came around in the 1950s. Now, prior to that, if someone went into cardiac arrest, the standard of care was to take a great big knife, open up their sternum, crack their ribs open like a book, and massage their heart by hand. There's a book by a guy named Sherwin Williams, who was a Sherwin Newland, who is a surgeon, and he had this great description of, as a medical student, a third-year student, he was in the hospital when a guy went into cardiac arrest. And as a third year, he had to grab a knife, slice this guy open, crack his ribs, and start massaging his heart. And as he's doing this, the description I remember him saying was, I started looking around trying to figure out who was screaming, because someone was screaming. And after a few moments, I realized, oh, it's me. So CPR is much better in the sense that we can actually keep the heart pumping. You might break some ribs, but that beats having all of them broken as you go through the sternum and crack it open. And so you can have CPR treatment, keep the blood moving, keep oxygenation possible until someone can get more definitive treatment. Now, Peter Safar is the person who came up with this, and I cannot imagine him getting this through the IRB of a research institution nowadays, because the way he proved it could work was he paralyzed the diaphragm of 31 volunteers and kept them alive with CPR in the meantime. I don't know what Plan B was in that experimental process. So he wrote this up, created the process of CPR, and focused on ABC, airway breathing compression, and also was instrumental in coming up with the Recessa Annie devices, using a Norwegian toy company to produce them, and that's how we still train. Now, if that weren't good enough, he actually moved to Pittsburgh and actually came up with the first ICU, kind of came up with a way that you could have the ICU paradigm in a hospital, and his daughter died because she had an acute asthma attack and couldn't get to the hospital in time. So he funneled that grief into something productive and created the first EMS service. And that obviously was such a good idea, it's now pretty much everywhere. So the idea that if you can get people to the hospital quickly, you have a chance of saving them. He did a lot of different things to make sure that people stayed alive. So Peter Safar, good name to know. Yet another radical jump, because I don't have a clean transition, sonar. In World War II, sonar was used to detect planes that were coming in. Sometimes it could be used to detect submarines underwater. Radar for planes in the air, sonar underwater. And a Scottish physician, Ian Donald, had been working with it during the war. And when he went back to practice, he had one of those extraordinarily bizarre thoughts that really panned out wonderfully. He thought, well, sonar's pretty neat, but we should see if we could make that thing work inside a person. And he came up with the first type of sonogram. So using sonar to create, using crystals to create waves that then bounce off structures and then are, sensed by the same probe that sent it out, is now possibly the thing that's going to replace the stethoscope as the sign of, hello, I'm a doctor. Having mobile sonographic units is going to be more and more common, which is why we're trying to make sure it's present in the curriculum, because it's something you're going to be seeing a lot more of. And this came around because somebody thought about sunken ships and thought, I should point that at a person. So there we go. Now, we're almost done. Targeted drug design was one of the final things that's occurred that really created a new paradigm of treatment. Everything I've mentioned, the vaccines, medical, instrumentation like sonograms, MRIs, they followed a similar paradigm, but the last new paradigm I can really throw at you before we're done is targeted drug design. We've talked about biological simples and compounds. We've talked about taking organic compounds from animals, from botanicals, isolating them. But targeted drug design goes the other way around. And this was in the 1960s. A physician from Scotland named James Black thought, well, we know that epinephrine binding to beta receptors is going to have an effect. What if we need to decrease that effect? What if we need to decrease the rate at which the heart is beating? Well, if we know what epinephrine looks like, maybe we can make another chemical from scratch that binds to that same thing but doesn't have the same effect. And so, looking at epinephrine, he was able to synthesize propanol, and that's going to be the first beta blocker. And now this is a major route that pharmacology utilizes to come up with new drugs, looking at the sites and effects of binding and coming up with things that are mimics to either inhibit, competitively compete with it, or overactivate certain receptors. Now, one of my favorite bits about him, in addition to this really clever idea, is that he was horrified to learn that he'd won the Nobel Prize in 1988 because he did not like being the center of attention. So maybe that's the key to getting the Nobel Prize. Really, really don't want it. Probably not. All right, thank you guys. We've went a little over time, but hope you enjoyed it. And our next talk is going to be on December 1st, and it is 2 hours. Usually it's 2 separate talks, but this year we combined them into one, and we'll be talking about the history of surgery from ancient times all the way up to the current era. And thank you once again.